So now we're going to the example number 3, which is the problem 1619 in the textbook. And here we have the instant shown. The arm AB has an angular velocity of the omega AB of 0.5 radian per second. And we have the angular acceleration of the alpha AB is equal to 2 radian per second. So we've been given the information at the point near the point A for the link AB. Now, demand what will be the angular velocity and the angular acceleration of the length CD, that the vertical one, okay, at this instant. So we start to, once again, sketch the 3-body diagram. But before again to show you that, I can obviously show you that when this link is going to go to that direction, we're going to have a velocity that's perpendicular to it. Okay. Now, and this movement is going to bring that link to that direction. And then we're going to have another velocity that's going to that direction. And we can see that these velocities actually are not parallel. So simply we can sketch a line from here, another line from here, and we can find the IC point. And from it, I can calculate what will be the omega of the link VC, and then I can find what will be the omega of the alpha of the link CD. So again, that's what we're going to do. The link AB will look like that. It's going to have, it does have omega and it has alpha, and this will help me to find the relative acceleration equation by finding first the velocity at B. We can find the tangential acceleration at the point B and the normal acceleration at the point B. Now we're going to the next link, which is going to be the horizontal link BC. Okay, so the BC will look like that. We have the same velocity. B is going to be at the point B, the same direction. Then we go to the link of the BIC, because we extend this one. And we are going to have on the other side, on that link, the VC is going to that direction, as we mentioned here. Okay, and we are going to have two components once again. One of them is going to be normal acceleration. It's going to have the same direction of the velocity at the point C, and we're going to have the tangential one. Actually, tangential is going to be on the same direction because tangential of that link. Okay, and normal is going to have the perpendicular direction to the link CD. So that will be the shape we're going to have. We are going to make the IC. We know the velocity at V, so I can find the omega of this link, which is going to be the omega VC. Then I can calculate the other parameters toward going back to the link CD. So the link CD, I'm sorry, the link CD is going to look like that. This is a vertical. Its omega should be to the counterclockwise, and the point C have the velocity and the tangential and normal accelerations. Now, that will be the case we are going to solve for. So you can see that actually sketching for the 3-body diagram is going to be a very important stage. Now, the known are going to be the angular velocity of the AB and the angular acceleration of the AB. The unknowns are first the acceleration at the point C. We don't know what the x direction and the y direction, or the normal and the tangential. And the alpha of the link BC is also unknown. Now we're going to the velocity, and the alpha CD is also unknown. We're going to the velocity B. Okay, we need to know what will be the x and the y direction of that, and this shouldn't be something actually hard to be done. And also for the velocity C, we know that the vertical component is going to be 0, and the horizontal component is unknown at that stage. And we don't know what the omega BC or the omega CD. So we're going to assume all positive if adopting a vector calculation, and we're going to write down the equations that we are going to use. So we are going to go from the link AB where we know the omega AB, calculate the velocity B and the omega BC. go to the link BC, calculate the VC, and then use that for the link CD to find the omega of the CD. The equation we're going to be applying is that, of course, you can use the IC method. The acceleration equation we're going to use for the from the link AB, we know the omega AB and the alpha AB. We can calculate the AB because we can find the tangential and normal acceleration. Okay, the omega BC can be found, and the alpha of the BC can be found. Go to the link BC. After know all this information, we can calculate the acceleration at C and put that on the link CD. We can find the alpha of the CD. Okay, so we're going to go with step by step. We start with the velocity analysis from the road AB, and the velocity at B is given to you as 0.45. So mainly is going to be equal to the omega multiplied by the RAB. Okay, so the direction of the velocity of the point B and the C are unknown, so we're going to have the location of the in a centimeter center can be determined as we mentioned earlier. And now for this triangle, we can, by using this triangle, we can find what will be the omega of the BC. If I know the omega of that link is going to be the same omega of the link BC. How can I find the omega of the link VIC? Simply, we are going to say that this velocity is perpendicular to it. If I know its length, I can find the omega, which is going to be the same omega. And finally, the velocity C, if I know the omega of the length VC, I can find the acceleration normal here. And also I can find the omega of that length, which is going to be the same omega of the link CD. Then I can find what will be the velocity at that point here. Okay, so you can see that the VB is going to be equal to 0.5 radian per second, which is the omega AB, multiplied by 0.9, which is the length of the link AB. The direction of the velocity at the point B and the C are known, and so the location of the IC can be determined. And from that, I can find the omega of the BC. So you can see how we found this one. Simply, we first divided the 0.2, sorry, 0.45 to be divided by the 0.2 multiplied by 0.2 divided by the sine 30, and we're going to find the value is going to be 1.125 radian per second. Now we're going to use this one to be multiplied by 0.2 and multiplied by tangent of 30, and we'll come out to the conclusion that the VC is going to be equal to 0.39 meter per second going to the left. Now we can determine the angular velocity of the link CD as well. The omega CD, well, actually, we calculated that. The omega CD, but with the known values that we're going to apply, which is going to be 0.39 meters per second, that's the velocity of the point C, and divided by 1.25, which is the length of the link the link CD. And now we found all the first stage of the parameter, which regarding to the velocity. Now let's go back to the acceleration analysis from the road AB. We can calculate the tangential and the normal accelerations. So for the first one, it's going to be alpha multiplied by the r. For the second one, it's going to be the omega square multiplied by the r. That's for the normal, that's for the tangential. Now we are going to go to the link CD. We are going to put the acceleration, that's the tangential, and that's the normal value. And we do have the omega, and we do have the acceleration C is going to be 0 to the vertical value. Now the ACN can be found. How we did that? How we got the value for the 1.122, we're going to use the omega squared multiplied by the r of the length CD. So the length CD is 1.25 meters. The omega of the CD has been found as 0.312. That's what we've done here. Okay, and then we're going to find that the normal acceleration of the point C is equal to 0.122 meter per second square. Now we're going to applying the relative velocity equation between the point B and C. So the AC is going to be equal to the AB plus the alpha of the PD multiplied by the RC slash B and minus the omega of the BC square multiplied by the RC slash B. Sorry, that's the omega BC, not BD. Okay, so here that should be BC. So now we're going to apply the equations and find the parameters for the x-axis and the y-axis. So the negative acceleration at the point C to the x-axis, which means that these are the i's, is going to be 1.8 negative multiplied by the cosine of 30 minus 0.225 sine 30 minus 1.125 square multiplied by 0.2. For the y-axis, we are going to repeat the same thing. What is going to be for the y-axis? So we already have the velocity normal known, and we are going to have it as negative 0.122. And we are going to use the y direction to find the alpha of the length BC. After we're going to find that, we're going to substitute in the equation before, and we're going to find the value for the acceleration of the C in the x direction. So by solving, you should get the value to be equal to 1.92 meter per second square. Or actually, I would like you to check this answer yourself to see if it's going to be correct or not. The alpha of the BC, the same from the second equation, is going to be equal to negative 4.14 radian per second square. Now we are going to continue doing the solution. Now we have the ACX and are going to be able to find what will be the value of the alpha we had for the length CD. So I'm going to go to the length CD. The tangential acceleration is going to be the ACX. So in that case, the RCD is known. This one is unknown because this one is known. So I can rearrange the equation and I can find that the alpha DC now can be solved. Again, to multiply the k by the I is going to be 0 for the j, and then we're going to have the k multiplied by the is going to be negative I multiplied by negative. I'm going to have negative 1.25 alpha DC is going to be equal to negative 1.9 I. So by solving that, I will get that the answer for the alpha CD to be 1.54 radian per second square. Okay, so once again, we just followed the procedure to solve the question. It doesn't have any complications. Maybe the increasing of the number of the links was the only disturbing that you may face in this question.